Good morning. Looks like 9:30 is getting earlier and earlier for everyone. Hello to all the people watching at home. I think there should be a requirement that if you're watching the video, you can only watch it 9:30 to 11 on some day. That just or at least start watching then. Just so you can all feel our mornings. Today we're going to talk about balanced search trees. Now, we've hinted at this for a while. Our goal today is to get a search tree data structure so we can insert, delete, and search, all in log n time per operation. So we want a tree that's guaranteed to be log n in height. So that's a balanced search tree data structure. We want a data structure that can maintain a dynamic set of n elements in log n time per operation. So let's say using a tree of height order log n. Now, if you look very closely, we haven't actually defined what a search tree data structure is. We've defined what a binary search tree data structure is, and that's one particular kind, and that's what we'll be focusing on today. In recitation on Friday, we'll look at, or you will look at, balanced search trees that are not necessarily binary. They can have, each node can have a constant number of children, not just two. Okay? So I'm defining this generally. You'll actually see what a search tree is in the general case later on. Today we'll just be focusing on the binary case, so I won't define this yet. There are a lot of different balanced search tree data structures. So these are the main ones that I know of. The first one was AVL trees. This was invented in 1962, so that was the beginning of fast data structures. The next three sort of come together, and this is what you'll cover in recitation this week. So these are non-binary trees. Instead of binary, we have maybe binary and tertiary, or binary or tertiary or quaternary, or a general constant degree B. So that's another way you can get balance. 2-3 trees were sort of the second trees to be invented. They were invented in 1970 by Hopcroft. The trees we'll cover today are called red-black trees. These are binary search trees and of guaranteed logarithmic height. Then there's some others. So skip lists are ones that we'll cover next week. It's not exactly a tree, but it's more or less a tree. And one that you'll see on your problem set this week are treeps, which I won't talk too much about here, but they're in some sense easier to get because they essentially just rely on the material from last Monday. Right, so on Monday, we saw that if we just randomly built a binary search tree, it's going to have log n height most of the time in expectation. So treeps are a way to make that dynamic, so that instead of just having a static set of n items, you can insert and delete into those items and still effectively randomly permute them and put them in a tree. So in some sense, that's the easiest. It's also one of the most recent search tree data structures that was invented in 1996. By a couple of geometers, Ryman Seidel and Aragon. So those are just some search tree data structures. The only ones we will not cover in this class are AVL trees. They're not too hard. If you're interested, you should read about them because they're fun. I think they're a problem in the textbook. Okay, but today we're going to focus on red-black trees. which is a fairly simple idea. Red-black trees. And it's a particular way of guaranteeing this logarithmic height so that all the operations can be supported in log n time. So they're binary search trees. And they have a little bit of extra information in each node called the color field. And there's several properties that a tree with color field has to satisfy in order to be called a red-black tree. These are called the red-black properties. And this will take a little bit of time to write down, but it's all pretty simple. So once I write them down, I'll say what they really mean. There's 4 properties. The first one's pretty simple. Every node is either red or black. That's hence the name of red-black trees. So the color field is just a single bit specifying red or black. And red nodes I'm going to denote by a double circle because I don't have colored chalk here. And black nodes will be a single circle. And you probably don't have colored pens either, so save us some grief. Red is double circle, black is single circle. And we sort of prefer black nodes in some sense. Red nodes are a pain, as we'll see. Okay, second property is that the root and the leaves are all black. And I'm going to pull a little trick here, or treat binary search trees a little bit differently than we have in the past. Normally you think of a tree as a bunch of nodes. Each node could have 0 or 1 or 2 children, something like this. I'm going to imagine appending every place where a node does not have a child. I'm going to put a little dot here, an external node which I call a leaf. So normally leaves would have been these items. I'm just going to add to every absent child pointer a new leaf. And these will be my leaves. These are really the nil pointers from each of these nodes. So now every internal node has exactly 2 children, and every leaf has 0 children. Okay, so these are the nodes I'm referring to. These guys are black, and this guy is black, according to rule 2. Now the properties get a little bit more interesting. The parent of every red node is black. So whenever I have a red node, its parent has to be black, a single circle. Okay. So in other words, if you look at a path in the tree, you can never have 2 red nodes consecutive. It has to be, you can at most alternate red, black, red, black. You can have several black nodes consecutive, but never 2 red nodes. Okay, and then one more rule. It says a little bit more about such paths. So if we take a simple path, meaning it doesn't repeat any vertices, from a node x to a descendant leaf, of x, all such paths to all descendant leaves have the same number of black nodes on them. So let me draw a picture. We have some tree. We have some node x in the tree. And I'm looking at all the paths from x down to some descendant leaf down here, the bottom of the tree. all of these paths should have the same number of black nodes. So here I'll draw that each one has 4 black nodes, the leaf, and 3 above it. We know that these, from property 3, these nodes don't have, at most half of the nodes are red, because whenever I have a red node, the parent must be black. But I want all of these paths to have exactly the same number of black nodes. One subtlety here is that the black height, I didn't really leave room, so I'll write it over here. This should be the same for all paths, but in particular, the count I'm interested in does not include x itself. Okay, so if x is black, I'm only calling the black height. So the black height of x is this count 4. And even if x is black, the black height is 4. So these are just some minor details to get all of the algorithms a bit clean. So let's look at an example of a red-black tree. So yeah, I'll show you an example, then I'll say why we care about these properties. Okay, so this tree has several properties. The first thing is that it's a binary search tree. Okay, so you can check an in-order traversal should give these numbers in sorted order: 3, 7, 8, 10, 11, 18, 22, 26. So it's a valid binary search tree. We've appended these leaves with no keys in them. They're just hanging around. Those are the nil pointers. So each of these you can call nil. They're all just marked there, wherever there's an absent child. And then I've double circled some of the nodes to color them red. Okay, if I didn't, the black heights wouldn't match up. So I have to be a little bit careful. From every node, we'd like to measure the number of black nodes from that node down to any descendant leaf. So for example, the nil pointers, their black height is 0. Good, that's always the answer. So these guys all have black height 0. I'll just represent that here. Black height equals 0. Okay, what's the black height of 3? 0, not quite, because these nodes are black. So the black height is 1. Okay, you're right that we don't count 3 even though it's black. It's not included in the count, but the leaves count. And there's only 2 paths here, and they each have the same number of black nodes, as they should. Over here, let's say 8 also has black height 1, even though it's red. Okay, same with 11. Same with 26. Each of them only has 2 paths. Each path has 1 black node on it. 10, what's the black height? Still 1, good. Because we don't count 10. There's now 4 paths to leaves. Each of them contains exactly 1 black node plus the root, which we don't count. 22, same thing, hopefully. Okay, this is getting a little more interesting. There's 1 path here which has 1 black node. There's other paths here which are longer, but they still only have 1 black node. So if we just sort of ignore the red nodes, all these paths have the same length. Okay, 18 should be bigger, hopefully. Black height of 2. Because each of these paths now has 1 black node here, 1 black node in the leaves, or 1 black node here and 1 black node in the leaves. And finally, the root should have black height of 2. Easier to see over here, I guess. Each of these paths has 2 black nodes. Same over here. Okay, so that's just, hopefully these properties make sense. We didn't check all of them. Every red node has a black parent. If you look at all of these paths, we sort of alternate red black at most, or we have just a bunch of blacks, but we never repeat 2 reds in a row. The root and the leaves are black. That we used pretty much by definition. Every node is red or black. OK, that's easy. This is a particular set of properties that may seem a bit arbitrary at this point. They will make sense, a lot more sense as we see what consequences they have. But there are a couple of goals that we're trying to achieve here. One is that these properties should force the tree to have logarithmic height, order log n height. And they do, although that's probably not obvious at this point. It follows mainly from this from all the properties. 3 and 4 are the main ones, but you pretty much need all of them. The other desire we have from these properties is that they're somehow easy to maintain. Okay, I can create a tree in the beginning that has this property. For example, I could make, I have to be a little bit careful, but I could make, certainly if I take a perfectly balanced binary tree and make all of the nodes black, it will satisfy those properties. Okay, this is a red-black tree. Okay, so it's not too hard to make these properties hold just from the beginning. The tricky part is to maintain them. When I insert a node into this tree and delete a node from this tree, I want to make it not too hard. In log n time, I've got to be able to restore all these properties. Okay, that will be the hardest part. The first thing we'll do is prove that these properties imply that the tree has to have height order log n. Therefore, all searches and queries on that data structure will run fast. Then the hard part will be to make sure these properties stay true if they initially held true when we make changes to the tree. So let's look at the height of a red-black tree. And from this, we'll start to see where these properties come from, why we chose these properties. So the claim is that a height of a red-black tree with n keys, so I'm not saying nodes here because I really only want to count the internal nodes, not these extra leaves that we've added, has height at most 2 times log of n plus 1, so order log n. But we have a pretty precise bound of a factor of 2. There's a proof of this in the textbook by induction, and you should read that. What I'm going to give is more of a proof sketch. You should read the proof by induction because all the practice you can get with proof by induction is good. The proof sketch, on the other hand, gives a lot more intuition of what's going on with red-black trees and connects up with recitation on Friday. So let me tell you that instead. I'm going to leave that board blank and go over here. So the first thing I'm going to do, this is I'm going to manipulate this tree until it looks like something that I know. The first thing the main change I'm going to make is to merge each red node into its parent. And we know that the parent of a red node must be black. So merge each red node into its black parent. So let's look at that here. So I'm going to take this red node, merge it into its parent, take this red node, merge it into its parent, and so on. There's one up there which I can't reach, but I'm going to redraw this picture now. So 7, so the top node now becomes, in some sense, 7 and 18. They got merged together, but no one else joined them. Then on the left, we have 3. Okay, nothing joined that, and there's some leaves as usual. Now, if you look at, maybe I'm going to have to draw this. Uh-oh. Heard that sound before. So I'm merging these nodes together. And I'm merging all of these nodes together, because each of these red nodes merges into that black node. And I'm merging these 2 nodes together, because I'm putting this red node into that black node. So now you can see from the root, which is now 7/18, there are 3 children hanging off. Okay, so in that picture, I'd like to draw that fact, assuming I can get this board back down. Good. So between 7 and 18, I have this conglomerate node, 8, 10, 11. And there are 4 leaves hanging off of that node. And off to the right, after 18, I have a conglomerate node, 22/26. And there are 3 leaves hanging off of there. Okay? Kind of a weird tree because we've dealt mainly with binary trees so far, but this is a foreshadowing of what will come on Friday. This is something called a 2-3-4 tree. And any guesses why it's called a 2-3-4 tree?
You can have 2, 3, or 4 kids.
Every node can have 2, 3, or 4 kids, yeah. Except the leaves, they have 0. Okay, there's another nice property of 2-3-4 trees. Maybe hinted at. So there's really no control over whether you have 2 children or 3 children or 4 children. But there's another nice property. Yeah.
The bottom, all of your children have the same depth.
All of the leaves have the same depth, exactly. All of these guys have the same depth in the tree. Why is that? Because of property 4. Okay. On Friday, you'll see just how to maintain that property. But out of this transformation, we get that all of the leaves have the same depth, because their depth now, or let's say their height in the tree, is their black height. The depth of these leaves will be the black height of the root. Okay, because we're erasing all the red nodes. And we said if we look at a path and we ignore all the red nodes, then the number of black nodes along that path is the same. Now we're basically just leaving all the black nodes. And so along all these paths, we'll have the same number of black nodes. And therefore, every leaf will have the same depth. Let me write down some of these properties. So every internal node has between 2 and 4 children. And every leaf has the same depth. Namely, the black height of the root. This is by property 4. Okay, so this is telling us a lot. So essentially what this transformation is doing is ignoring the red nodes. And then if you just focus on the black nodes, height equals black height. And then black height is telling us that all the root to leaf paths have the same length. Therefore, all these nodes are at the same level. Having leaves at the same level is a good thing, because it means that your tree is pretty much balanced. If you have a tree where all the nodes are branching, so they all have at least 2 children, and all the leaves are at the same level, that's pretty balanced. Okay, we'll prove some form of that now. I'm going to call the height of this tree h prime. The height of the original tree is h. That's what we want to bound here. So the first thing is to bound h prime, and then we want to relate h and h prime. Okay. So first question is, how many leaves are there in this tree? And it doesn't really matter which tree I'm looking at, because I didn't do anything to the leaves. All the leaves are black, so the leaves didn't change. How many leaves are there in this tree, and therefore in this tree? Sorry? 9. Indeed, there are 9. But I meant in general, sorry. In this example, there are 9. How many keys are there? 8. So in general, how do you write 9 as a function of 8? For large values of 9 or 8. Sorry? Plus 1, good. Correct answer by guessing. N plus 1. Okay, why is it N plus 1? Because whenever we have it, let's look at the binary tree case where we sort of understand what's going on. Well, wherever you have a key, there are 2 branches. And that's not a very good argument. Okay, but we have what is here called a branching binary tree. Every internal node has exactly 2 children. And we're counting the number of leaves that you get from that process in terms of the number of internal nodes. The number of leaves in a tree, a branching tree, is always 1 plus the number of internal nodes. You should know that. You can prove it by induction. Okay, so the number of leaves is n plus 1. It doesn't hold if you have a single child. It holds if every internal node has a branching factor of 2. Okay, this is in either tree. And now we want to pull out some relation between the number of leaves and the height of a tree. So what's a good relation to use here? We know exactly how many leaves there are. That will somehow connect us to n. And what we care about is the height. And let's look at the height of this tree. So if I have a 2, 3, 4 tree of height h prime, how many leaves could it have? What's the minimum and maximum number of leaves it could have? 2 to the h to 4 to the h, or h prime. So we also know in the 2, 3, 4 tree, the number of leaves has to be between 4 to the h prime, because at most I could branch 4 ways in each node. And it's at least 2 to the h prime, because I know that every node branches at least 2 ways. That's key. So I only care about one of these, I think this one. So I get that 2 to the h prime is at most n plus 1, because the number of leaves is n plus 1. We know that exactly. So we take logs of both sides. This is h1 is at most log of n plus 1. So we have a nice balanced tree. This should be intuitive. If I had every node branching 2 ways and all the leaves at the same level, that's a perfect tree. It should be exactly log base 2 of n plus 1. It turns out not quite n. That should be the height of the tree. Here I might have even more branching, which is making things even shallower in some sense. So I get more leaves out of the same height. But that's only better for me. That will only decrease the height in terms of the number of leaves. N plus 1 here was the number of leaves. So, cool. That's an easy upper bound on the height of this tree. Now what we really care about is the height of this tree. So we want to relate h and h prime. Any suggestions on how we might do that? How do we know that the height of this reduced tree is not too much smaller than this one? We know that this one is at most log n. We want this one to be at most 2 log n plus 1. Or we know the answer, right? We've said the theorem. Sorry? Right. So property 3 tells us that we can only have one red node for every black one. We can at most alternate red and black. So if we look at one of these paths that goes from a root to a leaf, the root to a leaf, the number of red nodes can be at most half the length of the path. And that's if we take the max overall paths, that's the height of the tree. So we know that h is at most 2 times h prime. Or maybe it's easier to think of h prime as at least a half h. Assuming I got that right. Because at most a half of the nodes on any root to leaf path are red. So at least half of them have to be black, and all the black nodes are captured in this picture because we only threw away the red nodes. So we have this relation, and therefore h is at most 2 times log n plus 1. Okay, pretty easy. But to remember, this tree has to be balanced and that they're not too far away from each other. Okay, so in Friday's recitation, you'll see how to manipulate trees of this form. There's a cool way to do it. That's 2, 3, 4 trees. Today, we're going to see how to manipulate trees in this form as red-black trees. And you'll see today's lecture and you'll see Friday's recitation, and they won't really seem to relate at all. But they're the same, just a bit hidden. Okay. So this is good news. We now know that all red-black trees are balanced. So as long as we can make sure that our tree stays a red-black tree, we'll be OK. We'll be OK in the sense that the height is always log n, and therefore queries in a red-black tree. So queries are things like search, find a given key, find the minimum, find the maximum, find the successor, find the predecessor. These are all queries that we know how to support in a binary search tree, and we know how to do them in order height time. And the height here is log n, so we know that all of these operations take order log n in a red-black tree. Okay. So queries are easy. We're done with queries. Just from balance. Not a surprise. We know that balance is good. The hard part for us will be to do updates. And in this context, updates means insert and delete. In general, in a data structure, we talk about queries which ask questions about the data in the structure, and updates which modify the data in the structure. And most of the time here, we're always thinking about dynamic sets. So you can change the dynamic set by adding or deleting an element. You can ask all sorts of questions. In priority queues, there were other updates like delete min. Here we have find min, but note we could then delete it. Okay, but typically these are the operations we care about. And we'll talk about updates to include both of these and queries to include all of these, or whatever happens to be relevant. In problem sets especially, you'll see all sorts of different queries that you can support. OK, so how do we support updates? Well, we have binary search tree insert, which we call tree insert. We have binary search tree delete, tree delete. They will preserve the binary search tree property, but we know they don't necessarily preserve balance. You can insert a bunch of nodes, just keep adding new minimum elements, and you'll get a really long path off the end. So presumably, they do not preserve the red-black properties, because we know red-black implies balanced. In particular, they won't satisfy property 1, which I've erased, which is every node is red or black. It'll add a node and not assign it a color. So we've got to assign it a color. And as soon as we do that, we'll probably violate some other property, and then we have to fix that property and so on. So it's a bit tricky, but you play around with it and It's not too hard. Okay, so updates must modify the tree. And they're going to do it to preserve the red-black properties. They're going to do it in 3 different kinds of modifications. The first thing we will indeed do is just use the BST operation, tree insert or tree delete. That's something we know how to do. Let's just do it. We're going to have to change the colors of some of the nodes. In particular, the one that we insert better be colored somehow. And in general, if we just rip out a node, we're going to have to recolor it. Recolor some nearby nodes. There's one other kind of operation we're going to do. So recoloring just means set to red or black. The other thing you might do is rearrange the tree, change the pointers, change the links from one node to another. And we're going to do that in a very structured way. And this is one of the main reasons that red-black trees are interesting. The kinds of changes they make are very simple. And they also don't make very many of them. So they're called rotations. So here's a rotation. Okay, this is a way of drawing a generic part of a tree. We have 2 nodes A and B. There's some subtrees hanging off, which we draw as triangles. We don't know how big they are. We know that they better all have the same black height if it's a red-black tree. But in general, it just looks like this. There's some parent and there's some rest of the tree out here, which we don't draw. I'll give these subtrees names, Greek names, alpha, beta, gamma. And I'll define the operation right rotate of B. So in general, if I have a node B, I look at it and I want to do a right rotation. I look at its left child and draw this picture, all the subtrees of those 2 nodes. And I create this tree. So all I've done is turn this edge 90 degrees. What was the parent of B is now the parent of A. A is now the new parent of B. The subtrees rearranged. Before they were both subtrees of, these 2 were subtrees of A, and gamma was a subtree of B. Gamma is still a subtree of B, and alpha is still a subtree of A, but beta switched to being a subtree of B. Okay? The main thing we want to check here is that this operation preserves the binary search tree property. Remember, the binary search tree property says that all the elements in the left subtree of a node are less than or equal to the node, and all the elements in the right subtree are greater than or equal to that value. So in particular, if we take some node little a in alpha, little b in beta, and little c in gamma, then A is less than or equal to capital A is less than or equal to little b is less than or equal to capital B is less than or equal to little c. Okay, and this is the condition both on the left side and on the right side. Because alpha is left of everything, beta is in between A and B, and gamma is after B. And the same thing is true over here. Beta is still supposed to be all the nodes that come between capital A and capital B. So this is good. We can definitely do this operation, still have a binary search tree, and we're going to use rotations in a particularly careful way to make sure that we maintain all of these properties. That's the hard part. But rotations will be our key. This was the right rotate operation. The reverse operation is left rotate. So this is left rotate of A. In general, of the 2 nodes that are involved, we list the top one. So it's right rotate of B will give you this, left rotate of A will give you this. So these are reversible operations, which feels good. The other thing is that they only take constant time. These are constant time operations because we're only changing a constant number of pointers. As long as you know the node B that you're interested in, you set the left pointer of B to be, you want it to be beta, so you set left of B to be right of A, and so on and so on. You make a constant number of those changes. You update the parents as well. It's only a constant number of links that are changing, so a constant number of assignments you need to do. Okay, you've probably seen rotations before, but we're going to use them in a complicated way. So let's look at how to do insertion. We'll see it 3 times in some sense. First, I'll tell you the basic idea, which is pretty simple. Mentioned some of it already. Then we'll do it on an example, feel it in our bones, and then we'll give the pseudocode so that you could go home and implement it if you wanted. Okay, this is, I should say, red-black insert, which in the book is called RB insert. Not for root beer, but for red-black. Okay, so the first thing we're going to do, as I said, is binary search tree, insert that node. So X now becomes a new leaf. We search for X wherever it's supposed to go. We create a new, shouldn't call it a leaf now. It's now a node hanging off. It's an internal node hanging off one of the original nodes. Maybe we added it right here. It now gets 2 new leaves hanging off of it. Has no internal children. And we get to pick a color for it. And we will pick the color red. Okay, why red? We definitely have to pick one of 2 colors. We could flip a coin. That might work, but it's going to make our job even messier. So we're adding a new node. Okay, it's not a root or a leaf, presumably, so we don't really need it to be black by property 2. Property 3, every red node has a black parent. That might be a problem. So problem is if its parent is red, then we violate property 2. Parent might be red. Property 3, sorry. Okay, the good news is that property 4 is still true, because property 4 is just counting numbers of black nodes down various paths. That's really the hard property to maintain. If we just add a new red node, none of the black heights change. None of the number of black nodes along a path changes. So this still has to hold. The only thing we can violate is property 3. That's reasonable. We know we've got to violate something at the beginning. We can't just do a binary search tree insert. Okay. So let's give it a try on this tree. I should say how we're going to fix this. How do we fix property 3? We're going to move the violation of 3 up the tree. So we're going to start at node X and move up towards the root. This is via recoloring. Only thing initially we'll do is recoloring until we get to some point where we can fix the violation using a rotation. And probably also recoloring. Okay, so let's see this algorithm in action. I want to copy this tree, and you're going to have to copy it too, so I'll just redraw it instead of modifying that diagram. So we have this nice red-black tree, and we'll try inserting a new value of 15. 22 is black. '22 is the new black. Okay, that should be the same tree. So now I'm choosing the number 15 to insert because that will show a fairly interesting insertion. Sometimes insertion doesn't take very much work. We just do a rotation and we're done. Here I'd like to look at an interesting case. So we insert 15. 15 is bigger than 7. It's less than 18. It's bigger than 10. It's bigger than 11. So 15 goes here. So we add a new red node of 15. And it has 2 black leaves hanging off of it. Replaced 1 black leaf. Now we have 2. Okay. Now, we violate property 3 because we added a new red child of a red node. So now we have 2 consecutive red nodes in a root to leaf path. We'd like to make this black, but that would screw up the black heights because now this node would have 1 black node over here and 2 black nodes down this path. So that's not good. What can we do? Well, let's try to recolor. Recolor. Yes. This always takes a little while to remember. So our fix is going to be to recolor. And the first thing that struck me, which doesn't work, is we try to recolor around here. It doesn't look so good because we've got red stuff down here, but we've got a black node over here, so we can't make this one red and this one black. It wouldn't quite work. If we look up a little higher at the grandparent of 15, up here, we have a black node here and 2 red children. That's actually pretty good news because we could instead make that 2 black children and a red parent. Okay, locally, that's going to be fine. It's not going to change any black heights because any path that went through these nodes before will still go through the same number of black nodes. Instead of going through a black node always here, it will go through a black node either here or here because paths always go down to the leaves. So that's what we're going to do. Recolor these guys. And we'll get 10, which is red. We'll get 8, which is black. 11, which is black. And these things don't change. Everything else doesn't change. We're going to leave 15 red. It's no longer in violation. 15 is great because now its parent is black. We now have a new violation up here with 18 because 18 is also red. That's the only violation we have. In general, we'll have at most 1 violation at any time until we fix it. Then we'll have 0 violations. Okay. So now we have a violation between 10 and 18. Somehow always counterintuitive to me. I have to look at the cheat sheet again. All right. Really? Oh, no, okay, good. I was going to say, we can't recolor anymore. Good. Not that bad. So what we'd like to do is, again, look at the grandparent of 10, which is now 7, the root of the tree. It is black, but one of its children is black, the other is red. So we can't play the same game of taking the blackness of 7 and moving it down to the 2 children. Never mind that the root's supposed to stay black. We'll ignore that property for now. We can't make these 2 black and make this one red because then we get an imbalance. This one was already black. So now paths going down here will have 1 fewer black node than paths going down here. So we can't just recolor 7 and its children. So instead, we've got to do a rotation. We better be near the end. So what I will do is rotate this edge. I'm going to rotate 8 to the right. So that's the next operation. Rotate right of 18. Well, there'll be one more operation after this. So we rotate right 18. So the root stays the same, 7, 3, its children. Now, the right child of 7 is no longer 18, it's now 10. 18 becomes the right child of 10. Okay, we have 8 over here with its 2 children. 11 and 15, that subtree fits in between 10 and 18, so it goes here. 11 and 15. And then there's the right subtree, everything to the right of 18, that goes over here. 22 and 26. And hopefully I'm not changing any colors during that operation. If I did, let me know. Okay, looks good. So I still have this violation, still in trouble between 10 and 18, but I've made this straighter. Okay, that's what we want to do, it turns out, is make the connection between 18, the violator, and its grandparent a straight connection, 2 rights or 2 lefts. Here we had a zigzag right-left. I'd like to make it straight. Okay, it doesn't look like a much more balanced tree than this one. In fact, it looks a little worse. But what we can do is now rotate these guys, or rather, rotate this edge. I'm going to rotate 7 to the left, make 10 the root, and then things will start to look balanced. This is a rotate left of 7. And I'm also going to do some recoloring at the same time, just to save me drawing one more picture. Because the root has to be black. I'm going to make 10 black immediately. I'll make 7 red. That's the change. And then the rest is just a rotation. So we have 18 over here. I think I actually have to rotate in order to keep some red-blackness here. Eight comes between 7 and 10, so it goes here. 11 goes between 10 and 18, so it goes here. 22 and 26 come after 18. Okay, now, if I'm lucky, I should satisfy all the properties that I want. Every node is red or black. Every red node has a black child. This is the last place we changed. Red nodes have black children. And all the black heights should be well defined. For every node, the number of black nodes along any node-to-leaf path is the same. And you check that was true before, and I did a little bit of trickery with the recoloring here, but it's still true. Okay, and you can check that just locally around this rotation. Okay, we'll do that in a little bit. For now, it's just an example. It's probably not terribly clear where these recolorings and rotations come from necessarily, but it worked. It at least convinces you that it's possible. And now we'll give a general algorithm for doing it. Any questions before we go on? So it's not exactly, just writing down the algorithm is not terribly intuitive. Red-black trees are the sort of thing where you play around a bit. You say, OK, I'm going to just think about recolorings and rotations. Let's restrict myself to those operations. What could I do? Well, I'll try to recolor. If that works, great. Pushes the problem up higher. And there's only log n levels, order log n levels, so that's going to take order log n time. At some point, I'll get stuck. I can't recolor anymore. Then it turns out a couple of rotations will do it. Always 2 rotations will suffice. And you just play with it, and that turns out to work. And here's how. So let's suppose we have a red-black tree and a value x we want to insert. Here's the algorithm. First, we insert it into the BST. So that we know. Then we color the node red. And here I'm going to use a slightly more precise notation. color is a field of x. And now we're going to walk our way up the tree with a while loop until we get to the root, or until we reach a black node. So in general, x initially is going to be the element that we inserted, but we're going to move x up the tree. If ever we find that x is a black node, we're happy, because maybe its parent is red, maybe it isn't, I don't care. Black nodes can have arbitrarily colored parents. It's red nodes that we worry about. And so if x is red, we have to keep doing this loop. Of course, just wrote the wrong one. While the color is red, we're going to keep doing this. So there are 3 cases, well, or 6, depending on how you count. That's what makes this a little bit tricky to memorize. Okay, but there are some symmetric situations. Let me draw them. What we care about, I've argued, is between x and its grandparent. So I'm using p of x here to denote parent of x just because it's shorter. So p of x is x's grandparent. Left of p of x is the left child. So what I'm interested in is I look at x, and if I don't assign any directions, x is the child of some p of x, and p of x is the child of the grandparent, p of x. Now, these edges aren't vertical. They're either left or right, and I care about which one. In particular, I'm looking at whether the parent is the left child of the grandparent. So I want to know, does it look like this? Okay, and I don't know whether x is to the left or to the right of the parent. But is parent of x the left child of p of x, or is it the right child? And these 2 cases are totally symmetric, but I need to assume it's one way or the other, otherwise I can't draw the pictures. Okay, so this will be, let's call it category A, and this is category B. And I'm going to tell you what to do in category A, and category B is symmetric. You just flip left and right. Okay, so this is A. So within category A, there are 3 cases. And within category B, there's the same 3 cases, just reversed. So what we're going to do is look at the other child of the grandparent. This is one reason why we sort of need to know which way we're looking. If the parent of x is the left child of the grandparent, we're going to look at the other child of the grandparent, which would be the right child of the grandparent. Call that node y. This is also known as the uncle or the aunt of x, depending on whether y is male or female. Okay, so this is uncle or aunt. Unfortunately, in English, there is no gender-free version of this, as far as I know. Parent, child, but no uncle, aunt. I'm sure we could come up with one. I'm not going to try. It's going to sound bad. All right. So why do I care about y? Because I want to see if I can do this recoloring step. The recoloring idea was, well, the grandparent, let's say it's black. If I can push the blackness of the grandparent down into the 2 children, then if both of these are red, in other words, then I'd be happy. Then I've pushed the problem up. This guy's now red. This guy's black. So these 2 are all right. This one may violate the great-grandparent, but we'll just keep going up, and that will be fine. So if we're lucky, y is red. Then we can just do recoloring. So if the color of y is red, then we will recolor, and I'm going to defer this to a picture called case 1. Okay, let me first tell you how the cases break up, and then we'll see how they work. So if we're not in case 1, so this else should be aligned with that, then we're either in case 2 or 3. So here's the dichotomy. It turns out we've actually seen all of the cases, maybe not A versus B, but we've seen the case in the very beginning where we just recolored, that's case 1. The next thing we saw is well, it was kind of annoying that the grandparent and 10, so 7 and 10 were not straight, they were zigzagged. So case 2 is when they're zigzagged. Turns out that's if X is the right of if X is the right child of its parent, and the parent is the left child of the grandparent, that's what we've assumed so far, that is case 2. Okay. The other case is that X is the left child of its parent. So then we have a left chain, X, parent of X, grandparent of X. That is case 3. Okay. I did not write else here, because what case 2 does is it reduces to case 3. So in case 2, we're going to do the stuff that's here, and then we're going to do the stuff here. If we're in case 3, we just do the stuff here. Or in case 1, we just do the stuff here. And then that finishes the 3 cases on the A side. Then up back to this if, we say else, this is case B, which is the same as A, but reversing the notions of left and right. Okay, in the natural way, every time we write left of something, we instead write right of something, and vice versa. So this is really just flipping everything over. We'll just focus on category A, and let's see what we do in each of the 3 cases. We've seen it in an example, but let's do it generically. Let's do it here. There's one more line to the algorithm, I should say. So aligned with here, we color the root. There's a chance when you do all of this, the root becomes red. We always want the root to be black. If it's red, we set it to black at the very end of the algorithm. This does not change the black height property. Everything will still be fine because every path either goes to the root or it doesn't. Every X to leaf path. So changing the root from red to black is no problem. It will increase the black heights of everyone, but they'll all stay. All the paths will still have the same value, just it'll be one larger. So let's look at the 3 cases. And I'm going to use some notation. Remember, we had triangles in order to denote arbitrary subtrees when we defined a rotation. I'm going to use triangle with a dot on top to say that this subtree has a black root. So when I fill something white, it means black because I'm on a blackboard. Sorry. Okay, and I also have the property that each of these triangles have the same black height. So this will let me make sure that the black height property 4, is being preserved. So let me just show you case 1. We always want to make sure property 4 is preserved because it's really hard to get that back. It's essentially the balance of the tree. So let's suppose we have some nodes C, left child A, right child B, and some subtrees hanging off those guys. And all of those subtrees have the same black height. So in other words, these things are all at the same level. Okay, this is not quite what I wanted, sorry. So I'm considering this is node X. X is red, and its parent is red. Therefore, we need to fix something. We look at the node Y, which is over here, and I'll call it, the key is D. The node is called Y. Okay, and it has subtrees hanging off as well, all with the same black height. So that will be true if all of these nodes are red, then all of these nodes have the same black height. And therefore, all of the child subtrees which have black roots all have to have the same black height as well. Okay, so we're sort of looking at a big chunk of red children subtree of a black node. Looking at all the stuff that happens to be red. In case 1, Y is red, so it participates. So another way to think of this is if we converted into the 2, 3, 4 tree, or tried to, we would merge all of this stuff into one node. That's essentially what we're doing here. This is not a 2, 3, 4 tree, though. We now have 5 children, which is bad. That's why we want to fix it. So we're going to recolor in case 1. And we're going to take C, instead of making C black and A and D red, we're going to make A and D black and C red. So C is red, A is black, D is black, and the subtrees are the same. B is the same, still red. Okay, now we need to check that we preserve property 4, that all of the paths have the same number of black nodes. That follows because we know we didn't touch these subtrees. They all have the same black height. And if you look at any path, like all the paths from A are going to have that black height. All the paths from C are going to have that black height plus 1, because there's a black node in all the left paths, and there's a black node in all the right paths. So all the black heights, all the black lengths are the same. So this preserves property 4. And it fixes property 3 locally, because B used to violate A. Now B does not violate anything. C now might be violated. So what we're going to do is set X. Our new value of X will be C. So it used to be B. We move it up a couple levels. Or in the original tree, yeah, we also move it up a couple levels. So we're making progress up the tree. And then we continue this loop. That's case 1. Recolor, go up. C may violate its parent, in which case we have to recurse. So we're recursing, in some sense, or continuing on C. So now let's look at case 2. So I'm still, in some sense, defining this algorithm by picture. This is some nice graphical programming language. So let's draw case 2. Yeah, I forgot to mention something about case 1. So I drew some things here. What do I actually know is true? So let's look at the algorithm, which I've now reversed. But we are assuming that we're in category A. In other words, the parent is the left child of the grandparent. So A is the left child of C. That much I knew. Therefore, Y is the right child. D is the right child of C. I didn't actually know whether B was the right child or the left child. It didn't matter. In case 1, it doesn't matter. Okay, so I should have said the children of A may be reversed, but it's just the same picture. Okay, I thought of this because in case 2 we care. So case 1 we didn't really care. In case 2 we say, well, case 2 is up there. Is X the right child of the parent or the left child? If it's the right child, we're in case 2. So now I can really know that X here is, which is B, is the right child of A. Before, I didn't know it and I didn't care. Now, I'm assuming that it's this way. Okay, y is still over here. And now we know that y is black. So y over here is a black node. So now if I did the contraction trick, all of these nodes, A, B, and C, would conglomerate into one. I only have 4 children. That actually looks pretty good. Y would not be involved because it's black. OK. So in this case, we're going to do a left rotation on A. So we take this edge, we turn it 90 degrees. What we get is A on the left, B on the right still. Should preserve the in-order traversal. C up top still. We have the Y subtree hanging off as before. We have one of the other 3 subtrees hanging off B, and the other 2 now hang off A. So this was just the generic rotation picture applied to this edge. Okay, what that does is before we had a zigzag between X and its grandparent. Now we have a zig-zig. We have a straight path between X. So X is still down here. I'm not changing X in this case, because after I do case 2, I immediately do case 3. So this is what case 3 will look like, and now I continue on to case 3. So finally, here's case 3, and this will finally complete the insertion algorithm. We have a black node C. We have a red left child from C. We have a red left grandchild, which is X. And then we have these black subtrees, all of the same black height, hanging off. Okay, which is exactly what we had at the end of case 2. So that definitely connects over. And remember, this is the only case left in category A. Category A, we assumed that B was the parent of X was the left child of the grandparent, here C. So we know that. We already did the case when Y over here is red. That was case 1. So we're assuming Y is black. Now we look at whether X was the left child or the right child. If it was the right child, we made it into the left child. X actually did change here. Before X was B, now X is A. Okay, and then case 3 finally is when X is the left child of the parent who is the left child of the grandparent. This is the last case we have to worry about. And what we do is another rotation, just like the last rotation we did in the example. That was case 3. So we're going to do a right rotate, in this case, of C. And we're going to recolor. Okay. So what do we get? Well, B now becomes the root, and I'm going to make it black. Okay, remember this is the root of the subtree. There's other stuff hanging off here. I really should have drawn extra parents in all of these pictures, because we're somewhere in the middle of the tree. Don't know where. Could be a rightward branch, could be a leftward branch. We don't know. C becomes the child of B, and I'm going to make it a red child. A becomes a child of B as it was before. Keep it red. And everything else just hangs off. So there were 4 subtrees, all with the same black height. And in particular, this last one had Y, but we don't particularly care about Y anymore. Now, we're in really good shape because we should have no more violations. Okay, before we had a violation between X and its parent, A and B. Those aren't even, well, A and B still have a parent-child relation, but B is now black. So, and B is black, so we don't care what its parent looks like. It could be red or black. Both are fine. We're no longer violating property 3. We should be done in this case. So property 3 is now true. If you want, you can say, well, x becomes this node, and then the loop says, oh, x is no longer red, therefore I'm done. We also need to check that property 4 is preserved during this process. Again, it's not hard because of the 2, 3, 4 tree transformation. If I contract all the red things into their parents, everything else has a constant, every path in that tree has the same length because they have the same black length. And over here, that will still be true. It's a little bit trickier here because we're recoloring at the same time. But if you look at a path that comes through this tree, it used to go through a black node C, and then maybe some red stuff, but I don't care. And then it went through these trees, which all have the same black height, so they're all the same. Now, you come in and you go through a black node called B, and then you go through some red nodes, doesn't really matter, but all the trees that you go through down here have the same black height, so every path through this tree will have the same black length, okay, if it starts from the same node. So we preserve property 4, we fix property 3. That is the insertion algorithm. Whew. It's pretty long. This is something you'll probably just have to memorize. You try a few examples, it's not so hard. We can see that all the things we did in this example were the 3 cases. The first step, which unfortunately I had to erase for space, all we did was recolor. We recolored 10 and 8 and 11. That was a case 1. 10 was the grandparent of 15. Then we looked at 10. 10 was the violator. It was a zigzag case relative to its grandparent. So we did a right rotation to fix that. Took this edge and turned it so that 10 became next to 7. That's the picture on the top. Then 18, which is the new violator, with its grandparent is a zig-zig. They're both going in the same direction. And now we do one more rotation to fix that. That's really the only thing you have to remember. Recolor your grandparent if you can. Otherwise, make it zig-zig. And then do one last rotation and recolor, and that will work. If you remember that, you can figure out the rest on any particular example. We rotate 10 over. That better be black, because in this case it's becoming the root, but we'll make it black no matter what happens, because there has to be one black node there. If we didn't recolor at the same time, we would violate property 4. Why don't I draw that just for kicks, because I have a couple minutes. So if we just did the rotation here, so say not the following. We take B. B is red. This will give some intuition of why the algorithm was this way and not some other way. And C is black. That's what we would have gotten if we just rotated this tree, rotated B, or rotated C to the right. So these subtrees hang off in the same way. Subtrees look great because they all have the same black height. But you see there's a problem. If we look at all the paths starting from B and going down to a leaf, on the left, the number of black nodes is whatever the black height is over here. Label that, black height. Whereas all the paths on the right will be that black height plus 1 because C is black. So now we violated property 4. So we don't do this in case 3. After we do the rotation, we also do a recoloring, so we get this. In other words, we're putting the black node at the top, because then every path has to go through that node. Whereas over here, some of the nodes went through C, some of them went through A, so this is bad. Right? Also, we would have violated property 3, but the really bad thing is we're violating property 4 over here. Okay, let me sum up a little bit. So we've seen if we insert into a red-black tree, we can keep it a red-black tree. So RB insert adds X to the set, to the dynamic set that we're trying to maintain, and preserves red-blackedness. So it keeps the tree a red-black tree, which is good, because that means we know then that it keeps logarithmic height. Therefore, all queries in red-black trees will keep taking logarithmic time. How long does red-black insert take? we know we're aiming for log n time per operation. I'm not going to prove that formally, but it should be pretty intuitive. So cases 2 and 3, sorry, pointing at the wrong place. Cases 2 and 3 are terminal. When we do case 3, we're done. When we do case 2, we're about to do case 3, and then we're done. Okay, so the only thing we really have to count is case 1, because each of these operations, recoloring, rotation, they all take constant time. So it's a matter of how many are there. Case 1 does some recoloring, doesn't change the tree at all, and moves x up by 2 levels. We know that the height of the tree is at most 2 log n plus 1. So the number of case 1s is at most log n plus 1. Okay, so the number of case 1s is at most log n. So those take log n time. And then the number of case 2s and 3s is at most 1 for one of these calls. Well, together 2s and 3s is at most 2. Okay, so log n time. Cool. The other thing that's interesting about red-black insertion is that it only makes order 1 rotations. So most of the changes are recolorings. Case 1 just does recoloring, no rotations. Case 2 maybe does 1 rotation. Case 3 does 1 rotation if you happen to be in those cases. So number of rotations is at most 2. It's either 1 or 2 in an insertion. It's kind of nice because rotating a tree is a bit more annoying than recoloring a tree. Why? Because if you have, say, a data structure, you have a search tree, presumably people are using this search tree for something. They're like making queries. For example, this search tree represents, I don't know, all the documents matching the word computer in Google. Okay, you've got a Google t-shirt up here. So let's use a Google reference. You have this search tree, stores all the things containing the word Google. You'd like to search maybe for the ones that were modified after a certain date or whatever it is you want to do. So you're doing some queries on this tree. And people are pummeling Google like crazy with queries. They get a zillion a second. Don't quote me on that. The number may not be accurate. It's a zillion. But people are making searches all the time. If you recolor the tree, people can still make searches. There's just a little bit you're flipping. I don't care in a search whether a node is red or black, because I know it will have logarithmic height. So you can come along and make your occasional updates as your crawler surfs the webs and finds changes. And recoloring is great. Rotation is a bit expensive because you have to lock those nodes, make sure no one touches them for the duration that you rotate them, and then unlock them. So it's nice that the number of rotations is small, really small, just 2, whereas the time has to be log n because we're inserting into a sorted list, essentially. So there's an n log n lower bound if we do n insertions. Okay, deletion, I'm not going to cover here. You should read it in the book. It's a little bit more complicated, but the same ideas. It gets the same bounds, log n time, order 1 rotations. So check it out. That's red-black trees. Now you can maintain data in log n time per operation. Cool. We'll now see 3 ways to do it.